Right now, somewhere in the cosmos, Einstein's equations are predicting something that makes physicists deeply uncomfortable. Not just strange, uncomfortable. And one of the greatest minds of the 20th century spent years wrestling with whether we should even believe what the mathematics is telling us. Richard Feynman had a problem with black holes, or rather, with what they meant for everything we thought we understood about reality. Because hidden in Einstein's general relativity equations, there's a prediction so bizarre that for decades, scientists hoped it simply couldn't be true, that nature would find some way to prevent it, that the universe had built-in safety rails. It doesn't. Let's start with what we actually know, not what makes us comfortable. Space is expanding. This isn't speculation or theory in the loose sense. We can measure it directly. Distant galaxies are moving away from us, and the farther they are, the faster they're receding. When we look at light from these galaxies, we see something peculiar. The wavelengths are stretched, shifted toward the red end of the spectrum. Why does this happen? Picture sound waves from a siren as an ambulance speeds away. The pitch drops because the waves get stretched. Light behaves similarly. An object moving away from you causes its light waves to elongate, shifting them redder. Astronomers discovered this pattern in the 1920s, and it revealed something profound. The universe itself is getting bigger. Now here's where it gets interesting. If space is expanding now, then rewind the clock. Everything gets closer. Keep going back. Denser, hotter, further still. Eventually you reach a point where everything that exists, every atom, every particle, was compressed into an infinitesimally small region. That moment we call the Big Bang. Not an explosion happening in space, but the explosion of space itself. But Feynman wasn't thinking about the universe as a whole. He was thinking smaller, much smaller stars. What happens when a star dies? For most of their lives, stars are in perfect balance. Nuclear fusion in the core generates outward pressure. Gravity pulls inward. These forces counteract each other for billions of years. But eventually, the fuel runs out. Fusion stops. And when it does, there's nothing left to resist gravity's pull. For smaller stars like our sun, this is relatively peaceful. They cool down, shrink into white. Dwarfs, dense spheres about Earth's size, then fade over trillions of years into cold stellar remnants. Massive stars, different story entirely. When a truly massive star exhausts its fuel, the collapse is violent beyond comprehension. The core implodes in seconds. Electrons get forced into protons, creating neutrons. You end up with a neutron star, a sphere the size of a city with more mass than our sun. The density defies intuition. A single teaspoon of this material weighs as much as a mountain. Drop something from just 1 meter above the surface and it accelerates to a substantial fraction of light speed before impact. But even neutron stars have limits. Around 1.5 solar masses, the Chandrasekhar limit. Below that threshold, neutron pressure can support the star. Above it, the collapse continues. And this is where Einstein's equations start predicting things that made Feynman and many others profoundly uneasy. Because when you compress enough mass into a small enough space, the mathematics describes something that seems physically impossible. A boundary appears in the calculations. A critical radius, different for every mass, below which the equations say time stops and space curves back on itself completely. We call this the Schwarzschild radius, named after Karl Schwarzschild, who derived this solution in 1916. For our sun, it's about 3 kilometers. For Earth, 9 millimeters. Normal objects are nowhere near these limits. The sun's actual radius is hundreds of thousands of kilometers. Earth is over 12,000 kilometers across. But what if you could compress the sun down to 3 kilometers, or Earth into a marble? You'd cross that boundary, that critical threshold, where the math stops behaving normally, where something genuinely bizarre emerges from the equations. In the mid-1960s, they called these objects collapsed stars. Some said frozen stars for reasons that become clear when you examine what the equations actually predict. Others called them dark stars, because no light can escape from within that critical radius. Most physicists hoped they simply couldn't exist, that nature had some mechanism to prevent matter from collapsing that far. Maybe stars would always explode violently enough to shed mass before reaching the critical threshold. Maybe something else would intervene. Feynman wasn't satisfied with hope. He wanted to understand what the equations were actually saying, even if the answers made everyone uncomfortable. Because if you take general relativity seriously, if you follow the mathematics wherever it leads, you encounter predictions that challenge everything intuitive about space and time. And the strangest prediction? What happens to someone who falls into one of these collapsed objects? Two observers, same event, completely different experiences of reality, both correct. That's where things get truly strange. Picture the scenario more precisely. A massive star collapses past that critical threshold. You're watching from a safe distance with your telescope. An astronaut stands on the collapsing surface. At first, everything seems normal. The star shrinks. The astronaut waves. Light reaches, you showing his movements in real time. But as the collapse accelerates toward the Schwarzschild radius, something disturbing begins. The light arriving from the astronaut's position shifts redder. His movements slow from your perspective. He waves his arm, but the motion stretches out, taking longer than it should, then longer still. This is gravitational redshift, combined with time dilation. Light escaping that intensifying gravitational field loses energy. Its wavelength extends toward the red end of the spectrum. Simultaneously, time itself runs slower, near intense gravity relative to distant observers. The closer the star gets to its critical radius, the more extreme these effects become. The astronaut's light dims. His movements crawl. Finally, as the surface reaches the Schwarzschild radius, he freezes completely. His image locked there at the boundary forever. Time has effectively stopped for him from your vantage point. He'll remain frozen at that edge for eternity, never quite crossing. His light redshifted into invisibility. This is why some physicists call them frozen stars. From outside, nothing ever crosses that boundary. Everything just stops there. But here's what makes this truly unsettling. Switch perspectives. What does the astronaut experience? Absolutely nothing unusual. His watch ticks normally. Time flows at its regular pace. The boundary approaches, and he crosses it smoothly. No jolt, no warning, no sensation whatsoever. Maybe it takes him 30 seconds from his perspective. Maybe 2 minutes. Some finite amount of time. He passes through the Schwarzschild radius without even noticing there was something to notice. Except now, something fundamental has changed. He tries sending a signal outward. Radio waves, light, beams, anything. Nothing works. Not because something's blocking the transmission, but because the geometry of space itself has warped so severely that outward doesn't exist anymore. Every possible path, every trajectory, every direction points inward toward the center. Space has curved back on itself so completely that escape is geometrically impossible. He's trapped. And he keeps falling toward the center where tidal forces grow infinite and mathematics collapses entirely. We don't know what happens at that point. The equations break down. From outside, you see him frozen forever. From his perspective, he fell through infinite time and faces certain doom. Both views are correct. They're not contradictory. They're two valid descriptions of identical physical reality, because time genuinely flows at different rates, depending on gravitational field strength. This sounds like abstract theory, but it's experimentally verified. Right now, your head ages faster than your feet. The difference is minuscule, but real. Your head sits slightly farther from Earth's center. Gravity there is fractionally weaker. Time runs fractionally faster over your entire lifetime. Your head ages roughly 90 billionths of a second, more than your feet. You'll never notice, but precision instruments can measure it. In 1960, the Pound-Repke experiment dropped a photon 22 meters down a tower at Harvard. They measured its frequency at the bottom. The frequency had shifted. The photon fell from a region where time runs slightly faster to where it runs slightly slower. The shift was incredibly tiny, about 1 part in 1,000 trillion. But they measured it, proved it definitively. Near a neutron star, the effect becomes dramatic. Time at the surface runs approximately half as fast as time far away. An hour there equals 2 hours for distant observers. Near the Schwarzschild radius of a collapsed star, the effect approaches infinity. An hour for someone falling in could correspond to billions of years for you watching from a distance. Technically, infinite time. This is why the falling observer appears frozen to you. From his frame, time flows normally. From yours, it's essentially stopped. Earth's core is younger than its surface, about 2.5 days younger, because time runs slower there in stronger gravity. Over 4.5 billion years, that accumulates to roughly 2 days difference. This isn't speculation or unproven theory. It's measured reality, confirmed by multiple experiments, as fundamental as any fact in physics. So if these collapsed stars actually exist, how would you detect them? They emit no light by definition. Light cannot escape from within the Schwarzschild radius. They're invisible. Dark voids where stars used to be. But there are methods, indirect approaches. First, look at binary systems. Most stars have companions, orbiting their mutual center of mass. If one collapses into a dark star, you'd observe something peculiar, a visible star, apparently orbiting empty space. Except it's not empty. Something massive and invisible pulls on that visible star. Watch carefully. Plot the orbit. Calculate the unseen companion's mass. If it exceeds the Chandrasekhar limit, if it's too massive for a neutron star, and if it's completely dark, you might have found one. Many stars exist in binaries. If collapsed stars are real, some must have visible partners. We should detect their gravitational influence. Second method involves gravitational lensing. Light bends around massive objects. Einstein predicted this in 1915. We confirmed it. During the 1919 solar eclipse, starlight passing near the sun curves measurably. A collapsed star would bend light far more dramatically. If light from a distant star passes close to 1, the light path curves around it. The collapsed star functions as a gravitational lens with perfect alignment. Collapsed star directly between you and a background star, you might observe something remarkable. The background star's light bends around the collapsed star from multiple directions. You could see distorted images, perhaps multiple copies of the same star, maybe even a complete ring of light. The probability of such alignment is extremely low. You need 3 objects lined up precisely: the collapsed star, the background star, and your telescope. All perfectly positioned. The odds are awful, but not impossible. We might observe this eventually if we photograph enough stars over enough time. Chance could deliver the right configuration. During the mid-1960s, some colleagues held views about collapsed stars that troubled me deeply. One common theory insisted stars simply cannot collapse below the Schwarzschild radius. They cannot become these frozen stars or dark stars. Some mechanism must prevent it. The reasoning went this way. If a star exceeds the Chandrasekhar limit, it will do something to avoid complete collapse. It will explode, shed mass in a supernova, anything to drop below that critical threshold. Because if it didn't, it would continue collapsing past the Schwarzschild radius. Nobody wanted to contemplate where that led. This reasoning bothered me profoundly. It doesn't explain why stars explode. It merely asserts they explode because they must avoid collapsing. That's circular logic. It's equivalent to claiming divine intervention causes supernovas, so we needn't worry about collapsed stars. That isn't physics. That's evading the question entirely. Another perspective, which I sarcastically called the all right, Jack theory, operated differently. I cannot observe inside the Schwarzschild radius. I cannot predict what occurs there. The mathematics breaks down at the singularity. So why should I concern myself? As long as I remain safe out here. All right, Jack. This attitude disturbed me even more. The observer falling inward faces a genuine problem, a real future, an actual fate. Just because we cannot observe it from outside doesn't render it unreal. It doesn't justify ignoring it. The question of what happens inside is genuinely difficult, extremely difficult. The mathematics is complex. Our physical intuition completely fails us. But avoiding the question isn't acceptable. This argument sidesteps everything without addressing anything. When physics predicts something strange, something deeply uncomfortable, we don't get to dismiss it merely because it's inconvenient. We must contemplate it, work through it, attempt to understand it. Even when the answers are bizarre, even when they're deeply unsettling. That's what physics demands. The question requires serious thought. Consider what's occurring right now somewhere in space. A massive star is collapsing, exhausting its fuel, gravity crushing it, smaller and smaller. If it's massive enough, if it surpasses that critical limit, it won't halt. It continues collapsing past the Schwarzschild radius, past the point where even light cannot escape. From far away, someone observing sees it decelerate, freeze. The star appears to halt. At the boundary, frozen there eternally, time itself has ceased from their viewpoint, but an observer on that star experiences nothing unusual. They cross the boundary in seconds, perhaps minutes. Normal time. Then they attempt to signal outward and cannot. They're trapped. Space itself is curved so completely that every direction points inward. Both observers are correct. Time genuinely flows differently for them. This isn't abstract philosophy. It's direct measurement. The Pound-Rebka experiment demonstrated it. Drop a photon 2 meters and its frequency shifts. Your head ages faster than your feet. Earth's core is younger than its surface. Everyone knows time flows, but you must pause and truly consider what that means. Time isn't uniform everywhere. It bends, stretches near intense gravity. It can decelerate to nearly nothing. And space is expanding right now. Galaxies racing apart. We can measure it directly, observe it in the redshift of distant light, reverse time, and everything collapses to a point. The Big Bang. Advance it forward and perhaps space expands eternally, or perhaps everything collapses back eventually. We don't know yet. Individual stars collapse. Perhaps the entire universe collapses or expands forever. The mathematics predicts all of this. Strange phenomena, uncomfortable realities. But mathematics doesn't care about comfort. It simply describes what exists. Some people want to avoid these questions entirely. Claim stars cannot collapse that far, must explode first. Or insist we shouldn't worry about what happens inside because we cannot observe it. But that's not physics, that's retreat. The question is difficult. The mathematics is challenging. Our intuition fails completely. But the answer, whatever it proves to be, is real. The observer falling inward has an actual fate. Time genuinely stops from one perspective while continuing from another. These aren't contradictions. Both are true simultaneously. That's the truly incomprehensible nature of reality. Space expands. Time bends, stars collapse into absolute darkness, and we're only beginning to grasp what it means when you genuinely think about it. When you really stop and consider what these equations reveal, the universe is far stranger than it appears on the surface. Not simpler, more complex, more unsettling. The mathematics doesn't offer comforting answers. It describes reality as it is, not as we'd prefer it to be. Feynman understood this. He knew that intellectual honesty demands we follow the logic wherever it leads, even when it takes us to places that feel impossible, even when every instinct screams that it can't be right, because the alternative, ignoring what the equations tell us simply because it makes us uncomfortable, that isn't science. That's wishful thinking. Right now, somewhere in the cosmos, a star might be crossing that boundary. Time splitting into two equally valid but utterly different descriptions of the same event. And whether we're comfortable with that or not changes absolutely nothing about whether it's true. The universe doesn't require our approval to be what it is.